Okay, well, good afternoon. I'm Eugene Spafford, and I'm on the faculty here at Purdue with computer science, and I am going to give you a talk on rethinking cybersecurity. And come on in. This is a talk that actually is based on a talk I was giving 12 years ago on some basic ideas in cybersecurity. And as a result of my sabbatical over the last year at some national labs and U.S. government facilities, I was encouraged to bring this back out, update it a little bit, and turn it into a current talk. So the idea behind this is talk a little bit about what is cybersecurity and what are some things that we should be thinking about in the way that we conduct research in the field. So first question, if we're going to talk about cybersecurity, we sort of know what the cyber part is, but how about the security part? When we're talking about a system being secure, what is it we really mean by that? How is it that we can identify features that have to be in place, and what is it those features should provide? So we'll start with an intuitive definition. Right? Rather than trying to delve into a formalism at first, we'll start with something that's intuitive, which is a system is secure if it's protected against all forms of threat. I mean, I think that's something that you can sort of resonate with. You can look at and go, well, that seems like a reasonable definition of security. So what are the kinds of threats we have to worry about if we're going to apply this as a definition? Random hackers breaking into our systems? Yeah, we can do that most of the time. Sure, we can secure against that. Malware? Probably. We're seeing some problems with things like ransomware. Keeping those out, but mostly we're able to stop the tens of thousands of new viruses and other malware that appear every day. Nation-state sponsored hackers, special cases. I would say that there's nobody in this room who could secure a system completely to keep out someone who has the resources of a nation-state behind their efforts. UFO invasion? No. I don't think anybody knows how to protect our systems against that. So there's a threat category we can't deal with. How about an extinction event meteor impact? No, that's beyond as well. That's a problem. Only in the movies can we deal with those. And interestingly, there was a news report about a week and a half ago that in approximately 7 years we may have to worry about this. Hey, 7 years, that's a long time. You'll get your degrees by then, I hope. So here's another kind of threat category that we don't know how to deal with. Well, maybe we could deal with it. Maybe if we go ahead and establish our Mars colonies and make copies of all our computing systems and the Mars colonies as backups, then we've secured our data at least. And no, we haven't, because eventually, we're going to have the heat death of the sun, and when that happens, the sun will slowly expand into a small red giant. The corona will engulf all of the inner planets, and goodbye to our data. Now that's several tens, hundreds of millions of years away, so we've got a little bit of time. We'll probably be running Windows 12 by then, but nonetheless, it's a threat. So what this really kind of illustrates in a way is that cybersecurity, at least by the definition I gave to start with, isn't that helpful because we can't really achieve it. We cannot protect our systems against all threats. And it exposes an underlying issue. Security, at its heart, is really an economics issue. It's not a technology issue. Because we can think of all kinds of wonderful technologies and we can deploy all kinds of wonderful technologies, but how much are we going to spend to minimize the risk to an acceptable level? We can never completely eliminate it, but what's acceptable as a level that we're willing to tolerate, and how much are we going to pay to get there? Using sort of conventional definitions, we can't ever get perfect security. Now, has anybody in here ever heard of Robert Courtney? No. Okay. Well, see, this is another issue that I have with the way we deal with security. We don't know our history. Robert Courtney was a major figure in the early era of computer security. He was IBM's first security manager, first security architect, and one of the early winners of the National Computer Security Award for the work that he contributed to the field. You won't find him published in scientific journals. You will find him cited in things like Internet Standards and a few other places. But one of his early presentations, he gave his 3 laws of security. And these are still important today. The first is that nothing useful can be said about the security of a mechanism except in the context of a specific application and environment. Something that is secure in one locale will possibly be meaningless in another. Something that we use, for instance, to secure your cell phone may be completely inappropriate and ineffective when applied against a legacy mainframe or a network router. Second, never spend more mitigating a risk than tolerating it will cost you. This is why we don't have, for instance, an uninterruptible backup power supply on every computer we own. It's something that we can tolerate, and it's cheaper than putting that UPS system in place. And the third one is something that people who work in technology do not understand well. It's a management issue. And that is, there are management solutions to technical problems, but no technical solutions to management problems. You can, for instance, set rules around how certain things are to be used to avoid harmful or potentially dangerous circumstances. But building technology doesn't solve some management problems, because those are management and people and allocation of resources and priorities and other kinds of things that the technology can't touch. So as you learn about the technology, you also need to think about context and about the people and mechanisms in which those technologies are used. So let's do another attempt at trying to define security, and maybe we can do a better job understanding some of this as context. And what I'm going to do is go back and look at one of the older definitions in the 1970s, 1980s, which was around the time that the Trusted Computer Security Evaluation Criteria, the TCSEC, or the Orange Book, was written, and a lot of research was done by various academics and government researchers. And the idea is to look at a computer system as a set of state transitions. So I'm assuming all of you have had enough computing background to think about a computer as, at an instant in time, a set of values in memory locations and registers. And as the computer's clock ticks at a very high rate of speed, those contents change and define a new state of the system. There may be a lot of memory and a lot of registers, and so the state is very large. It's a tuple of potentially billions of different locations, but nonetheless it is a finite state. And theoretically we can define a set of allowed states where many of those memory locations maybe don't care, but we can define a set of states of the system that are okay, they're safe. And as the system executes and as it changes state, what we want for a secure system is that it always transition to another allowed state. So allowed state, allowed state, allowed state, great, we never leave that, we're always safe. That is potentially a safe or a secure system. This implies that there are other states which are bad states, harmful states, disallowed states. And we don't want any of these to occur. We don't want to find at one of those time slices that the computer system is in one of those states. And this is, again, part of that definition of security. Stay in the allowed states, avoid the bad states. Not only avoid entering them, but we don't want to stay in them. If we go in there and we stay there, that's potentially a really big problem. The notion of allowed states was mapped to the notion of formal specifications of computing systems. Again, and this is back in the 70s and 80s, and to a little bit in the 90s. And the idea in software engineering was to build systems that stayed in the defined, allowed, specified states. And this applied to both system safety and security. If we allow the system to execute in a state that isn't in the specification, that's a fault. Some fault led to entering a bad state. And if that happens and it stays that way, or it produces the wrong kinds of outputs or behavior, that's a failure. And a failure in a system that we want to be secure, or a protected system, is a security failure. So all of this was formally defined. And you can find it in the literature. There's a whole lot of work that was done at this time to define software engineering terms and system construction terms and the idea of a verified system. Along with this came the realization that there are a whole set of undefined states. And these are states the system might enter. We don't know if it will or not, because, of course, the behavior of the system is undecidable. But these undefined states aren't specified. They're neither good states, for sure, nor are they defined disallowed states. Entering one might lead to a fault, might then lead to misbehavior, but we don't know. You could also think of these undefined states as I don't know states. They might not be bad, but they're not necessarily where we want to be. And undefined states, it's possible we could enter the execution in an undefined state and then return to a good state without ever entering a disallowed state. And so they're kind of, well, we don't know, but they're not bad. But still, they lead to okay results. This is what most software probably looks like. And I'm limited by the amount of space on the slide to actually show the undefined states. Because when we're talking about potentially billions or trillions of memory locations and components in the execution of a program, executing at many millions of instruction cycles per second, it's very difficult to say exactly what all the allowed states are necessarily. And current software in all its complexity and components is undoubtedly largely undefined. In fact, I would argue, and I think we can safely say, that for most software you use, everything is undefined, because vendors have never done a formal specification. You have never seen a formal specification for Word or Excel or Safari or whatever, Android, whatever you're using, in all likelihood, because they haven't been done. We have general requirements, which are a first step, but no detailed specifications to say exactly what the good states and the bad states are of the system and how it should behave. There's a whole subfield involved with formal specifications, but it's both design and verification of that design that go to the heart of doing that specification and determining if it's correct using mathematical methods. It's currently quite time-consuming to do this, and it is expensive as a result, because you have to have additional software. It takes longer to program. It takes longer to check. It's much more difficult to modify after a system has been designed and built, because you have to go back and redo all of the verification, and it requires some extra expertise, among other things. So we don't have a lot of systems that are designed to this level of care. Usually it's aerospace, nuclear power, and some defense kind of applications that use this kind of very heavyweight process. Now, industry practice, that is the things you use on a regular basis. And I realize that for many people in the audience, this one reference is terribly dated, and I apologize. But on the left is kind of where industry is now. There are programs that say, we'll teach you to program in 12 weeks and get a high-paying job in industry. And they do. You have software firms hiring people whose total background in computing is learning how to program from a book like this. It shouldn't be a surprise why software, come on in. Sorry. It shouldn't be a surprise why software regularly crashes, misbehaves, and discloses information, is because many of these companies hire people with no background, really, to speak of. And this dated reference. If you go to Netflix and you get the movie Jurassic Park, I assume it's on Netflix, but you watch it, you'll see that there's the eccentric billionaire who spares no expense to recreate dinosaurs, buy an island, and equip it with an amusement park. And he hires one sloppy IT guy to run the whole place. And of course, disaster ensues and hilarity and T-Rex. But that's kind of what happens in industry. That's current practice, is that many companies will spend huge amounts on flashy new hardware, on new features, back-end databases, advertising, and almost nothing on security and verification. So the consequence of design is we end up with things like on the right, where it was just going to be a laser printer before we started adding features. Vendors feel the need to continue to add new complicated features to their product because they want people to continue buying the new release and the new version without any thought about how they really fitness to purpose or how they fit in with the original design. And as a result, things fail. There's a quote from the halcyon days of formal verification and specification from a journal that doesn't exist anymore, the Scientific Honeyweller. In fact, Honeywell doesn't quite exist the same way anymore. They used to make mainframe computers. And it's this quote: "A program that has not been specified cannot be incorrect. It can only be surprising." That's actually the state of things today. We are in a constant state of surprise. It isn't that the systems are incorrect. It's we didn't expect them to do what they did because they've never been specified. So how do we know what correct behavior is? How do we know what allowed behavior is? And that's a key concept that you need to bear in mind when we start talking about security of things like Android or like Firefox or anything else that we're going to run on our system. They weren't specified to behave in any particular way. We're simply finding ways that are surprising not only to us, but to the designers. And that's a problem. And if you end up doing research in this area, Young and Boebert in particular did a lot of work in this area. Earl Boebert is still around and still a character to talk to. He's retired, but no less cranky. This is a metaphor for the current software we have. We started off with a very simple set of things we wanted it to do, usually, and we keep adding to it, and we keep adding patches and new features until we get to the point where it is scary to actually go in and modify. Now, the story I heard when I first found this picture, you can see here in this, there is a trouble light hanging from a bundle of wires. And I was told that if you take the light off, the change in weight causes something in the system to misbehave. And they don't know what it is. So they keep the light there, it's not even plugged in, simply so that they don't have to track it down and figure out what the problem is. That's the equivalent of the software that we're using today. And in part it's caused by this very bad feedback cycle that is economic in nature. If you think about your systems that you use, eventually they get slow, and maybe they don't run the latest software release, or memory gets full. So what do? You save up and you go out and you buy a new computer system that's got 16 times the memory and it runs at 4 times the speed and everything's great again. You can port over all your software and run it, it's fast. And because it's fast, you can now go out and buy more software and add more data, and eventually it's slow again. And you have to buy more hardware. But to buy the hardware, you're going to buy hardware that can run all the software that you've already paid for and invested in and know how to use. So you're not going to go with a new operating system and new security features and new hardware that has well-partitioned execution. You're going to get something that's compatible with the system you have. And so is business. And so is government. And so is everyone else. And then the software you buy has to run on the hardware and the operating system that you've got. And so you just repeat the cycle. It's all because of this sunk cost. No one wants to break out of this cycle because it's too expensive to do so, even if we know the technology is better. Windows was designed in 1987. That's how old the system is that you're working with. It's over 30 years old in terms of its concepts. And yet, everything that we do now is still compatible with that first early version of Windows, because people have been accumulating the software over time. They don't want to train people new. They don't want to port things. It's become a huge millstone around our necks, effectively, to use that kind of Intel-based original architecture and the Windows platform on it. Now, yes, we have moved to some other platforms, right? We've got the Linux platform, all 570 versions of it, including Android subversions off in another corner. And we've got the Mac OS and iOS and a few others. And thankfully, for some really critical applications, we're running operating systems like Integrity. Anybody ever heard of Integrity? The operating system. No, probably not. It's a commercial operating system. They charge for it. They charge a lot of money for it. But it also is embedded in satellites, it's embedded in power plants, and it's embedded in airplanes, things that if they go wrong, people die and lots of money gets lost. It is a very, very secure, highly tested, verified operating system. There are a few like that are out there that you probably won't encounter because, well, we can't afford them here at Purdue, and the places that you're likely to go work are still stuck in this cycle and don't want to use something else. Now, I'll say open source may be worse because what happens is something breaks and the community says, gosh, how could that happen? The software was available for many eyes to see for years. Why didn't we see that? Well, the answer really is because most people are figuring out how to port the software to their new toaster rather than looking for problems in the existing software. And so everybody else says, all right, well, let's go ahead and fix it, and we all make it safe again, again and again and again. If you look now, the operating system kernel that is most dangerous in terms of security problems is not Windows. I mean, it hasn't been for years. Microsoft really focused in on software design lifecycle and verification and fixed that. It's Linux and Android that are the most dangerous systems right now because there are so many different versions, so many people writing for it, so many different applications that require privilege to run that we are constantly running into problems with those. So again, let's go back and look at this cyber what? What is cybersecurity? I was working at a DoD lab, and so one of the places I turned was the DoD definition that was undoubtedly developed by a committee and signed off on by political appointees. You don't ever want to have to use one of these unless you're bidding on a DoD contract because they're wordy, and I mean, if you look at this, it's terribly verbose. It's not terribly useful. And if you've taken any security courses and you talked about confidentiality, integrity, availability, you can see that this includes a whole lot more. And I'll talk about that more in a moment. All right, well, here's a few other definitions. So the first one, Rob Joyce, someone well-known who works at the National Security Agency, earlier this year in a publication said, cybersecurity is everything that results in protecting information and underlying technology from theft, manipulation, and disruption. That's not a bad definition, particularly within the confines of what has to be done by that agency. I came up with this other definition because I wanted to include the idea it's both science and practice. And it's protecting information and information processing components from misuse during their design, creation, transmission, storage, transformation, use, and disposal. So when you take a class such as 526 being taught by Professor Garman, there are aspects in there about how do we securely dispose of computers and electronic media. How do we design them? How do we buy them? These are all issues that go into a definition of security. Back in the 70s and 80s, and still to this day, we have the notion of assurance. And assurance is the science and practice of increasing our confidence, that is our trust, in the information security of a system. And that's related to what we do as security, is the idea of how to assure the security. We need to use both security and assurance together because we can't have perfect security, but we can increase our trust arbitrarily. And I included here, I was reminded of this in a conversation a couple days ago. Back in 1990, Simpson Garfinkel and I came up with this definition that a computer is secure if you can depend on it and its software to behave as expected, which is sort of similar to the first definition that I started off the presentation. But it's how the definition has evolved, and my own understanding of security has evolved over time. So that assurance bit, that trust bit, is something that was focused on for quite a while. We talked about cyber trust, we talked about cyber assurance throughout the 90s and the early 2000s, and I just included here some dictionary definitions of what trust is. And trust seems to fit with both the definition that I gave back in 1990 and the idea of trying to increase our trust in a system's security. Is we want to believe in the truth, the reliability, and the strength of the system. We want people to be able to use it and value its behavior and understand how it is. That if we put something into the safekeeping of the system, we can depend on the system to provide for it. And we aren't simply relying on luck. So for that trust alignment, for that ability to have that assurance and trust, I put this in here to stress, this goes back to Courtney's laws, the idea of trust alignment. Because when we're going to say we're going to trust something in the system, we have to be sure we understand what trust means. Each of us as individuals has values and goals about the things we want to do, about the information we have. There are things that I value as information that I want to protect. Okay. My employer, in this case Purdue University, also has things that it values and wants to protect. Your grades, for instance. My payroll information, not so much. Your grades, much more. These are things that are valued and okay. And then there are social and government goals and values about what we hold dear, what is legal, and those kinds of issues. And all of these exist out in the world. And what we want to do is have this ideal trust alignment so that at least as far as systems go, that whatever the system supports and enforces, it does for all of these where they overlap. So that what it protects on the system are my goals and values, and Purdue's goals and values, and society's goals and values, rather than just some of them. But that's the problem, is that most vendors don't have a good conception or a way to tailor the system, and you end up with something that supports a very divergent set of values and goals. Usually, not always, but usually, it's the values and goals that the programmers have, which may not be yours. If those programmers or their supervisors happen to be working for a criminal enterprise or another government, which are sometimes the same thing, what you get is a system that may not have any correspondence with your values and goals. It will be a system that you can't assure because you don't know what it's intended to support. And this gets back to the idea of specifications again. We have a problem because, once more, the vendors aren't telling you what goals and values they're supporting. The only goal and value that's immediately obvious is confuse the user with a 50-page end license agreement and get your money for the next upgrade. Well, those are not necessarily values that we're going to embrace, and they certainly don't represent the full universe of values that we want to have in the software. We don't have anything expressed that we can measure, that we can check against. And they are especially bad in a business or work environment where my values are based on me getting stuff done. I'm supposed to either write a program or turn in something for a grade or evaluate a proposal. The employer has security regulations about what I'm allowed and not allowed to do to get my work done. I have to have passwords that are 93 characters that include 15 special characters and a blood type. That's not going to support my work and getting work done. And if those don't match the underlying law and policy of where I'm working, it gets even worse. So we have a real problem here in assuring systems because we also don't have an understanding of what to trust and what the values are. And then, how do we compound trust? How are we going to do this? Because we build systems on top of other systems. We build software on top of hardware. We build applications on top of that software. And the hardware is built using components from other places. So we have this problem of compounding different items together and understanding anything about trust, assurance, or security of the end product. We sometimes talk about this as a supply chain issue. It's actually more than supply chain, but that's where it shows up, is taking different components and putting them together, especially components that someone else has produced and that we now have to assure in some way. So maybe we can define some tunable attributes so that we can decompose security and trust and evaluate them separately and then pull them together again. Well, to do that, let me revisit something from Lord Kelvin. And I keep meaning to look up why the name is Kelvin when his name was Thomson, but just take it. He was Lord Kelvin. His real name was William Thomson. And he wrote this about 250 years ago. When you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely, in your thoughts, advanced to the stage of science. And of course, I think the majority of you are here in computer science. You're interested in the scientific pursuit of something relating to computing. According to Lord Kelvin and lots of other people who've looked at philosophy of science, if we can't measure it, if we can't repeat it, if we can't compare it, it's not really science. We're still kind of doing alchemy, where we're throwing things into a pot and seeing what happens. Or we're throwing print statements into a program and see what comes out. Think about things we measured, especially in engineering disciplines. We're able to measure height, width, density, strength, boiling points, lots of things that we can measure. We don't have measures that we can apply in the area of security outside of cryptography. In cryptography, we have some good measures, but it really doesn't apply anywhere else. If we look at security as it's commonly defined in a lot of textbooks, we have these traditional properties of confidentiality and availability and integrity, which, by the way, Bob Courtney came up with. And Bob came up with it 20 minutes before a presentation he had to make to a set of IBM field engineers. Management said, you have to convince them that IBM's new operating system supports security in a way that no one else does, and you have to find a way that they can convey it to customers. That's a pretty tall order. Well, he thought about it a bit and took a piece of plastic, transparency. Only some of us have ever had experience with presentations with those, and proceeded to draw out this a kind of a triangle where he had confidentiality, availability, and integrity. And he went out and he presented this, and it really caught on with the field engineers because it was simple. They could present it to their customers, and there was a certain cachet in the 1970s, 1980s of talking about how we support CIA. There was a pun there, and they kind of that was kind of fun, and so it caught on. But there is no scientific basis for this classification, none at all. And yet we're using it as the basis for when we talk about our field of security. It's not a good model because the measures aren't orthogonal. Integrity overlaps availability. Availability overtakes confidentiality. Any one of those three can be used to disable the other of the third, and they don't have natural measures. I would argue that if we used rock, paper, scissors, it would be about as good as the CIA model. would have about as much value. Few people have tried to make it better. Don Parker, another. How many of you have heard about Don Parker before this slide went up? Okay, well, Don Parker was another giant in the field. And Don came up with this idea of, well, maybe there's 6 properties we need. And he argued this fairly well in a paper. I think there's some there is some insight here when we talk about being able to control something or whether it has utility, whether it's authentic. But even so, these measures are not orthogonal and they don't have natural units. What are 5 units of control? How do I add 2 more units of integrity? There's nothing here that we can actually point to and map and measure in a way that makes any sense. So what properties do we need? And I would say that the first thing that we need is we need correctness. We need to know that a system does what we designed it to do. Now that means that we have to be able to specify the design, we have to build the design, and then we have to verify the design. And whatever system we design should do nothing more than what we designed it to do. That's where security comes in. Right? Correctness, simple correctness, is that the system does what we designed it to do. But security comes into play when the system does other things that we didn't design. It does more. And sometimes it does more that we didn't plan on. But I would say that correctness is the first property, the fundamental property that we have to have. Beyond that, well, we want to support that composability I was talking about. We want to talk about trust. Simplicity is important because that goes into both design, modification, and use as well. We want simple systems. We want specificity. Instead of too much generality results in systems that either don't do things well or do too many things. And limiting the interactions of the system, both to what's currently out there and to anything new we might introduce. Other features that we might want, and I've included some here about for access control, interface, resilient failure modes. So if something goes wrong, the system just doesn't roll over and give up everything. Standardized hardened functions, non-subvertible auditing. There's a whole set of features here. Are they necessarily first-order features? I don't know, because I can't give you an exact list. This is a research agenda that needs to be pursued. And it needs to be pursued soon, because if we don't know what security is and what the important features are, we are going to continue to build systems that fail. And that's a fundamental problem. I don't know anyone who's really focused in on this. This is a DARPA level project, and I just haven't seen anybody take this on yet in a meaningful way. To come up with properties that are measurable and well-defined, they have some context that fits, so that we can take 2 systems, measure a quantity, and say that one is better than another, or worse than another, or that they're equal, according to some measure, that then, if somebody on the other side of the world takes the same 2 components and applies the same measurement regime, they get the same results. Because if we get different results when different people try the experiment, that's not science. That's luck. It's random. So we are not to that point as a field yet. Now, I'm not terribly disappointed by this, because one could argue that security really as a focus area is less than 50 years old. That's not quite 2 generations. And we're still learning in the area of mechanical and structural engineering, for instance. And that's been around for about 3,000 years. So we got a ways to go yet, but we really need to focus on this if we're going to have it as a science rather than an art. So let me give you some takeaways from this, some things that I would say are conclusions that I can draw from all of this. The first is one size doesn't fit all, and this is an important principle, and it really relates back to Courtney's 3 laws. And unfortunately, we don't recognize this in practice. Everybody wants to have a general purpose system. Everybody wants to build on top of Linux or Windows, or in a portable system, IoT, we want to build on top of Android. So it's not a matter of fitness for purpose. It's not a matter of tailoring for need. It's not a matter of limiting. It's a matter of, well, it's free or it's cheap and we already have it and somebody else has used it and we can reuse their code. That's not good reasons to build something to make it secure. I have this picture on the right. That's an actual artifact. I'm not going to call it a tool. That's made by the Wenger company. You can order it through Amazon. In fact, that's where I got the image. You've seen Swiss Army knives, I assume. No respecting member of any military would carry one of these. It has one of everything that they make and every possible tool, plus a whole lot others that they just thought of. It's just including a radio transmitter and left-handed scissors and all. It's just incredible. It's very pricey too. But as I look at this and I was going through this, you could take apart your automobile or build a house with one of these. It's got all the tools. But would you want to? Not if you knew what you were doing, because you wouldn't do a very good job and it wouldn't be very fast and you'd probably bruise your fingers pretty badly several times along the way. But this is what we do with saying, oh, we're going to build everything on top of a Linux Android base. We have this thing that does everything, including many things poorly, and the fact that we already have it means we're going to use it. That's not the same as having a toolbox of tools specially designed for the purpose at hand. So I would argue to you, this is one of the problems that we have, is this economic issue that we haven't yet learned how to overcome. And I'm not suggesting that your next homework assignment, you design a new operating system to do it. That's probably overkill, unless it's an operating systems class, and then maybe you might get extra credit. But we should start thinking about the assumptions we make in building everything on top of Java or C++ on top of an Android platform. That's not necessarily good craftsmanship. Second, quality first. There are a lot of things we can overcome by going back and patching, but quality is not one of them. Every time you apply a patch, the quality actually goes down. And if you don't get it right at the beginning by doing careful design, you really can't recover well from that at all. And we've learned that in the physical world, as by example here, but we've also continued to learn that in the virtual world. Third, if you don't specify what you're building, you're stuck with whatever you build. And that means whatever bad side effects it may have. This looks beautifully done. Probably reinforced concrete, nice rail. The next time the train comes through, it's not going to look as nice. They're stuck with it because they didn't really think about what it was they were building. Fourth, this is a variation on the classic picture. Software is not something that can be added in after the fact. You have to think about security when you do the design. And safety, and quality, and reliability. Those should be design parameters, not add-ons. So here are a set of goals, research goals. I'll put these forward for any of you who are looking for research topics. We need a comprehensive, clean definition of a secure system and its properties. That whole definition, what is security? What does it mean to be secure? We need a good definition that people can get behind. Then we need a sound set of metrics that match to those goals and those design parameters so that we can measure if we've accomplished it. Then we need a set of user-friendly systems for requirements capture, consistent with those two. Then we need a set of specifications, development, and testing compatible with number 3. Then we need coding systems that are compatible, that also support maintenance and aren't really painful to use. I've used some painful tools. Wouldn't wish it on others. And then we need V&V, verification and validation tools that support 4 and 5. And all of this with user-centric design. And this is the goal state. This is where we'd like to be. This is aspirational. This is where we should be as a field. But until we have these things, we can't get there. If all we do is continue to add on to and patch existing things with existing languages, existing compilers, everything's built with a GNU C compiler on top of Android using C++, we're never going to get there because we're going to inherit all the old problems and be blind to some of the ones that are there. I leave it to you because many of you in this room are the ones who are going to go on and define what security is. And the question is, how are we going to define it? I haven't given you a final definition, and I don't think I can because it remains to be done. That is really at the heart of this. How are we going to define security? And with that, I'll say thank you, and I think we have a few moments if you want to have questions or comments. If you want to ask a question or make a comment, the microphone on the desk in front of you has a little on button that you press and the green light will go on, and that's to ensure that it gets on the broadcast, on the recording. So turn on your mic and fire away.
If we are making a standard based on security, that would be done by which system has the most vulnerabilities compared to the other systems, or maybe the rate at which these vulnerabilities occur. But if that's constantly fluctuating, it's a difficult question in general. It's almost like trying to put a standard on technology in its current state because it's always going to continuously move. So I feel like we would need a new technology that could evaluate the current existing technology because it needs to be dynamic.
Dynamism certainly is going to be important in evolution. We do have standards that evolve. But I think part of the problem there is lumping everything together. We need to look some at threats. So what you're going to do as playing a game on your cell phone while you're waiting in someplace versus a system that's running command and control in a battlefield environment, using the same system for each, really vulnerabilities are different and the evaluation has to be different there. So we have, that goes back to Courtney's first law about understanding something about context and threats. A second aspect is we can actually anticipate a lot of kinds of threats. We know how to do things like threat trees and penetration analysis and fault hypothesizing that we could apply. And some things we can also do some formal mathematical verification. So I don't think the problem is quite as big as what you may be envisioning, but I don't know that it has a single overarching solution either. I think we're going to have to carve off parts and start looking at those. So maybe real-time systems is one thing and portable systems is another. Maybe. I don't know. I've been looking at this problem for a while and I don't think I'm up to it. I'm hoping somebody else is. Other questions or comments? All right, well, thank you. Remember to sign in on the sign-in sheet if you're registered for credit and do that each week. This talk will be up on the websites, YouTube and iTunes in a few days if you want to look at it again because you slept through it the first time. And thank you all very much for attending.